Jai Hind everyone. My name is Abhishek Gupta and I am working as an assistant professor in mechanical engineering department of Ajay Kumar Gar Engineering College. Today I will cover one of the complex topics on ferrous alloys of material science subject. This topic I actually cover uh, various topics like allotropic transformation of pure iron, iron carbon diagram, different phases of iron carbon diagram, iron and iron carbide diagram, features of iron and iron carbide diagram, three-phase reactions, and the microstructures of eutectoid steels, hypoeutectoid steels, and the hypereutectoid steels. So with the help of iron and iron carbon diagram, you can actually predict how, with the change in the percentage of carbon, how iron changes its phases on changing on at a different temperature level. So coming on to the firstly allotropic transformation of pure iron. What is actually the allotropic transformation? Allotropic transformation denotes the different phases of a particular materials like iron. When we cool the particular material from higher temperature to lower temperature in a particular span of time, then we can see that different phases of iron can be seen at different temperatures. So you can see that the melting point of iron is around 1539 degrees centigrade. So above 1535 degrees centigrade, every iron particle is in liquid state. And as we go on cooling this iron, then we can see that this solid phase has been formed, and this solid phase is known as delta iron, which is actually in the BCC structure. This delta iron temperature ranges from 1401 degree temperature to 1535 degree temperature. Then second is the gamma iron. This gamma iron is also known as austenitic phase, and this has abscisic structure, which is actually in non-magnetic, and the temperature ranges from 910 degrees centigrade to 1401 degrees centigrade. Then on further cooling, we can see that the alpha iron BCC structure has been seen, which is actually non-magnetic, and this alpha iron temperature ranges from 768 degrees centigrade to 910 degrees centigrade. On further cooling the iron, we can see that the alpha iron BCC structure has been seen, which is actually the magnetic phase. So depending upon the on cooling the material from higher temperature to lower temperature, different phases of iron has been seen, and these different phases of iron on cooling for a particular span of time, which shows different phases, this terminology is known as allotropy. So this allotropic transformation shows various phases of iron, and various behavioral properties has been seen at different temperature. So with this topic we can see how the materials behaves in a different manner when the temperature is increasing from particular 700 degree temperature to 1400 degree temperature. So coming on to the iron carbon diagram, the exact name is iron and iron carbide diagram. So this is the map of temperature at which different phases changes occur on very slow heating or cooling in relation to the carbon. So on y-axis temperature is there, and on n-axis the carbon percentage is increasing. So iron carbon diagram shows the type of alloy formed under very slow cooling, and proper heat treatment temperature can also be seen here in case of iron carbon diagram. This iron carbon diagram also shows that how the properties of steel and cast iron are radically changing by increasing the temperature or by decreasing the temperature or by going through particular heat treatment. Then second is the first allotropic phase is the ferritic phase. This ferritic phase is also known as alpha solid solution, and it is the interstitial solid solution of a small amount of carbon dissolved in alpha iron. and this alpha iron is in BCC form. This is the stable form of iron which we actually see below 912 degrees centigrade, and the maximum solubility is a 0.025 percentage carbon at 723 degrees centigrade, and it dissolves only 0.008 percentage carbon at room temperature. So at room temperature you can see that the carbon dissolubility in iron is only 0.008 percentage. So it is the softest structure that appears on the iron carbon diagram. So this is the softest structure which we actually see in the iron carbon diagram. Rest all the phases which we actually see in the iron carbon diagram has greater hardness in comparison to the ferritic structures. Then second is the perlite. Perlite is actually the eutectoid mixtures containing 0.8 percentage carbon and is formed at 723 degrees centigrade on very slow cooling. So on very slow cooling you will see the perlitic structure, and this is also known as eutectoid mixture because this perlite is generally formed at eutectoid temperature which is around 723 degrees centigrade, and this is a very fine plate like or laminar mixtures of ferrite and cementite. You can see that this is ferrite and this is the cementite. These sticks are you seeing. So there is the alternate layer of ferrite and cementite which actually constitutes the perlite, and this perlite is actually a little silver shiny in color, and this white ferritic background or matrix contains thin plates of the cementite. This cementite is actually in dark color and light color actually shows the ferritic part. Then third phase of iron carbon diagram is a austenitic phase. Austenitic phase is the interstitial solid solution of carbon dissolved in gamma iron. It is actually some ductile in nature, and this is one of the very good phases you can say, which possesses very good formability property that can be utilized into various particular applications. It has a maximum solubility you can see is around 2% of carbon at 1130 degrees centigrade. So you can see that the iron is maximum dissolved in this carbon has maximum solubility of 2.0 percentage at a temperature of 1130 degrees centigrade. Below that temperature you will not see any dissolubility of carbon in iron. It is normally not stable at room temperature because this type of phases is actually formed at a higher temperature, whereas the room temperature is around 36 or 35 33 degrees centigrade. So but under certain condition it is possible to obtain austenitic property at room temperature by heat treatment process. So coming on the fourth phase, which is cementitic phase, or it is also known as iron carbide. So Fe3C is also known as cementite, and it is very hard, brittle and intermetallic components of carbon and iron, and this is represented by Fe3C, which contains 6.67% carbon. It is the hardest structure that appears on the diagram, and the exact melting point is unknown. Its crystal structure is orthorhombic. It has low tensile strength, which is approximately 5000 psi, but very high compressive strength. So you can see that how different types of properties is actually seen in case of cementite. It is one of the hardest phase which we actually see in iron carbon diagram. Then another phase mixture is there, which is ledobrite. This ledobrite is not actually the phase, it is known as the phase mixture, and this ledobrite is actually formed at eutectic temperature, which is around 1130 degrees centigrade, and the carbon percentage is 4.3%. So this ledobrite is the eutectic mixture of austenite and cementite. Austenite means gamma phase and cementite means Fe3C phase. So then another phase is the martensitic phase. The martensitic phase is the supersaturated solid solution of carbon in ferrite, and it is formed at a very low temperature, which is around 200 or 300 degrees centigrade, and it is formed when we cool the steel in a very rapid manner. So you can cool the steel so cooled rapidly that it changes from austenite to martensite in such a manner that perlite formation is suppressed. Then only we can see the formation of martensite. Otherwise, if this perlite transformation is not suppressed, then perlite will be formed, not martensite. So the interstitial carbon atoms distorts the BCC ferrite into a BC tetragonal structure, which is responsible for the hardness of the quenched steel. So this interstitial carbon atoms actually distorts the BCC ferrite into a BCC tetragonal structures. Then only the hard form of martensite is actually seen in case of iron carbon diagram. So this is the actual final iron and iron carbon diagram. You can see, whereas y-axis shows the temperature and the x-axis shows the weight percentage of carbon. So up to 2.14 percentage, from 0 percentage to 2.14 percentage is known as steel, whereas from 2.14 to 6.70 is known as cast iron. Below 0.76 percentage, it is known as hypoeutectoid steel, and from 0.76 to 2.14 percentage, it is known as hypereutectoid steel. From 2.14 percentage to 4.30 percentage, it is known as hypoeutectic cast iron, whereas from 4.30 to 6.70 percentage, it is known as hypereutectoid cast iron. So this iron and iron carbon equilibrium diagram actually shows different phases of iron at different temperature. And this you can see one phase is seen perlitic phase, this is alpha phase, this is austenitic phase, this is a delta phase. There you can see ladderite gamma plus Fe3C. Here you can see alpha plus Fe3C, which is known as perlite. Here you can see cementite. Exact melting point of cementite is actually unknown, but the melting point of iron is around 1538 degree temperature. So you can see that the maximum solubility of carbon in iron you can see at a temperature of around 1147 degree temperature, 1147 degree, and the maximum solubility of carbon in alpha phase you can see is 0.022, and the maximum solubility of austenite phase of carbon in austenitic phase you can see is 2.14 percentage. So you can see that this is the liquidus line actually, and this is the solidus line. Everything above liquidus line is liquid, and below liquidus line you can see here everything is in solid phase. This is the austenitic phase, here is liquid phase, in between you will form gamma plus liquid phase. Here Fe3C is there, here liquid is there, so here liquid plus Fe3C you will see. Here delta phase is there, here liquid phase is there, so you can see delta plus Fe3C, Fe3C. Here gamma phase is there, here delta phase is there, so here you will see delta plus gamma. So you can see there are three different reactions which you will see in this iron carbon equilibrium diagram. First is the eutectoid reactions, which is occurring at 0.76 percentage of carbon and at temperature of around 727 degree temperature, where this gamma austenite one solid converts into two solids, that is alpha and Fe3C, which is also, this mixture is known as perlite. Second reaction is known as eutectic reaction. This is eutectoid reaction, this is eutectic reaction, where one liquid converts into two solids. One solid is austenitic phase and second is in cementite phase. Mixture is known as lead-aboride. Then third reaction, you will see that this is the peritectic reaction, whereas this delta plus liquid on cooling or heating converts into austenitic phase. So these are the three reactions: peritectic reactions, liquid plus delta gives austenitic; eutectic, liquid phase converts into austenitic phase and cementite phase; and eutectoid, this austenitic phase converts into alpha phase and cementite phase. So these are the different phases present: liquid, delta, this is in BCC structure and this is paramagnetic. Then another is the gamma austenite, which is FCC structure, this is non-magnetic. Then this is alpha ferrite, which is BCC structure and ferromagnetic, it is fairly ductile. And then another is the Fe3C, that is cementite, its structure is orthorhombic, it is hard and the brittle. So you can see that the maximum solubility of carbon in ferrite is 0.022% and the maximum solubility of carbon in austenite is 2.11%. So coming on to the different different reactions, like peritectic reactions occurs at 1492 degrees centigrade with low weight percentage of carbon alloy. Almost no engineering importance is there. Peritectic reactions occurs at a very high temperature, and these types of materials are those materials. These type of materials forms an alloy only when these two materials have shown the melting point temperature difference is very high. Then another is the eutectic reactions, which is actually at 1130 degrees centigrade with 4.3% weight percentage carbon, and the alloy formed is also known as cast iron. Eutectoid reactions occurs at 723 degrees centigrade, which is also known as eutectoid compositions of 0.8% carbon. Two phase mixtures are actually seen, that is, one is the ferritic and another is the cementite. This is known as the steel. So you can remember the eutectic with cast iron and eutectoid with steel. So you can see that this is the figure for peritectic reaction, whereas this delta plus liquid, there is delta, so in between it is delta iron plus liquid, and here is austenite. When delta plus liquid cools down, then the austenitic will be formed, and on heating this austenitic phase converts into delta plus liquid. Here delta iron is 0.10% carbon and liquid at 50%. On cooling gives austenitic at 0.18% carbon. Then you can see that eutectic point is the point when one liquid converts into austenitic plus cementite. Austenitic is gamma, cementite is Fe3C. This temperature is also known as eutectoid temperature, which is around 1130 degrees centigrade, or in some books 1140 degrees centigrade. And these reactions occur at 4.3% carbon, and on cooling converts into austenitic 2.1%, 2.0%, or cementite, which is around 6.67%. Cementite is formed at when the carbon dissolubility in iron is maximum at 6.67%. This mixture is known as lead-aboride. It is also known as eutectic mixture because this mixture is formed at eutectic temperature, which is around 1130 degrees centigrade. Then third diagram you can see, that is eutectoid reaction. This austenite converts into alpha ferrite plus cementite, gamma austenite, and this reaction actually occurs at 723 degrees temperature, and this is the carbon percentage, which is 0.8% of carbon. Austenite converts into ferrite plus cementite. Then the iron carbon diagram shows three horizontal lines which indicates the isothermal constant temperature reactions. on heating or cooling. First horizontal line we draw at 1492 degrees temperature, which is known as peritectic reaction, where peritectic reactions actually occurs where liquid plus delta converts into austenite. Second horizontal lines we actually see at 1130 degrees centigrade, where eutectic reactions take place, where liquid converts into austenite plus cementite. And the third horizontal line is at 723 degrees centigrade, where eutectoid reactions take place, where austenites convert into perlite, and perlite is the mixture of ferrite plus cementite. So in the last we will see the various microstructures of eutectoid steels. So I have already said that eutectoid steels actually forms at 727 degree temperature and at 0.8% carbon dissolvability. So you can see temperature on y-axis and a carbon percentage on x-axis. So when you draw one composition line, so you will see that there are x-axis dash, there is one point A and another point B. This A point is above the 727 degree temperature and this B point is below 727 degree temperature. Above this line 727 degree temperature, iron shows different phase, and below 727 degree temperature iron shows different phase. This A point shows austenitic phase, whose phase structure has been seen like this. And on cooling down you will see that a perlite is formed, and this perlite is the combination of alpha ferrite plus cementite. It is the alternate layer of ferrite plus cementite. You can see this is red is alpha and this strip blue color is the cementite. Here is the alpha. So this is the microstructure of for an iron carbon alloy of eutectide composition at 0.76% weight percentage carbon. Then this is the microstructure for hypoeutectoid steel. I have already told you that when the carbon percentage is below 0.8%, then the steel is known as hypoeutectoid steel. So below 0.8% carbon, when we draw one composition line, then three different phase structure has been seen at one at C, one at D, one at F. So one at C you will see that everything is in austenitic phase, then austenitic structure will be formed. On coming to the D, this region actually corresponds to alpha plus gamma, because here is alpha, here is gamma, then here will be alpha plus gamma. So some alpha particles will nucleate at the grain boundaries, which is actually shown by these red dots. Then on further cooling, this alpha particle will grow significantly and it will form one strip. And on further cooling below 727 degrees centigrade, you will see that a mixture will be formed of perlite, which is actually the combination of alpha ferrite plus cementite. Here you can see some eutectoid alpha is there, here pro-eutectoid alpha has been seen, and here Fe3C is seen. So you can see here 100% perlite is there. Here it is the mixture of it is also known as pro-eutectoid. So this is the schematic representation of microstructure for an iron carbon alloy of hypoeutectoid composition containing less than 0.76% weight percentage carbon, as it is cooled from within the austenitic phase region to below the eutectoid temperature. Then this is the microstructure of hypoeutectoid steels when we cool them from austenitic temperature to the perlitic temperature. Then coming on to the hypereutectoid steels, when carbon percentage is from 0.8% to 2.1%, and when you draw the one composition line, then this composition line actually divides the curve in three regions. One is this and this. So in this region, when you take one point, then everything is in austenitic phase. That's why all austenitic phase, homogeneous austenitic phase has been formed. When we cool down at point H, then you can see that Fe3C points nucleates, and on further cooling, this Fe3C points grows and it actually forms the pro-eutectoid Fe3C and eutectoid Fe3C and alpha perlite. So you can see this type of microstructure is actually seen when we cool down from G point to I point. So this is the complete microstructure diagram of iron carbon equilibrium diagram, and this complete structure shows different lines. Like you can see this A1 line is denoted at temperature 727 degrees temperature. This A2 line is there. This is the A3 line. This is the A4 line. This is the ACM line, and this at different composition line has been drawn at different temperature, and different composition line shows different structure. Like this shows austenitic phase, this shows austenitic plus cementite, this shows pro-eutectoid Fe3C, eutectoid Fe3C and alpha. Similarly, here you can see the hypoeutectoid steels, here eutectoid steels and there hypereutectoid steels. Below 2.1% everything is in steel, and above 2.1 to 6.7% everything is in the cast iron. Thank you, class. If you have any query regarding this, you can mail me at guptabhishek@akgec.ac.in. Thank you.